Okay, good afternoon, everyone. Can you hear me? Hello, Hanika, hello. Yes, I have seen your comment here. Okay, so I can see three of you are here. Okay, so let's wait for others to join. We'll start. Yes, hello, Uday, hello. Hello, Abhijit. Yes, welcome, Abhijit, to the session. Hi. So whoever is attending my session, don't forget to give a like. Okay. So four participants are there as I can see now on my screen. So those who are there, please give a like, and if you're new, then subscribe. Okay. So let's start. Right in the group, once Telegram group. If you are not there in the Telegram group, then you please join the Telegram group. Okay. So let's start with the topic for today. So what is our topic? All of you know what is your topic for today? Topic for today is our topic for today is the magnetic effect of electric current. So very easy, right? So let me tell that if you have any questions, then you are told to send your questions in the above given link. Magnetic effects of yes. Okay, let me change it. This link. This is the link. So you are told to send your question in this link. Okay. Okay. So send the questions in this link. I am pasting the link in the chat. 1 minute. Slides. Just a minute. Just sorry. I am putting this in the chat. Slides dot app dot gov dot gl. So everybody please join. Write in the Telegram group to tell the others to join fast. Okay, I have pasted the link, but the link will not work. You have to you use this link. Okay, if you will paste it in the Chrome, you will directly come to this, so you can ask your question in this group. Fine. Okay, so shall we start? Let me know, dear. Shall we start? Okay, so let me just write in the Telegram. Yes, okay. So let me write in the Telegram group once, then I'll start. Okay, so let us start. I've written the Telegram. Let's start now. Okay, so today we'll be going to start with a topic of magnetic effect of electric current, and a very easy topic. So first of all, what you can see on your background? What can you see on your background? What can you see on your screen? Rather, tell me what can you see on your screen? Tell me what you can see on your screen. What can you see on your screen? Write it in the live chat. Let me see. What can you see on your screen? Write in the chat. Magnetic field. Okay. Of which planet, dear? Which planet? Hans Christian. No. Where can you see Hans Christian? No. No, not Hans Christian. This is a structure of the magnetic field of Saturn planet. Okay. This is Saturn planet is here. This is the magnetic field of Saturn. Okay. Magnetopause. This is the pause. That means Yes, Saturn. Yes. So this is the magnetopause. That means the magnetic field is still here. Some extent the magnetic fields come till here. That is the normal compressed. This is, yes, Saturn's magnetic field. This is termed as compressed Saturn's magnetopause, and this is the normal magnetopause. Okay. So along with reading the chapter, we'll be dealing with this also. Very interesting topics also. So this is solar wind. That means the wind that is coming from the sun is termed as, here is termed as solar wind. Okay. So if you have any questions, send me in the link that is given. Okay. So today's topic for today is magnetic effects of electric current, class 10, lecture 1. Okay. So what topics we'll cover today, that I have given in the description. So check out which topics we are going to cover. In the description it is mentioned which topics I'll cover for today. Okay. So I can see four of you are there. What happened to the others, I have no idea, but you can invite others. We have a menti at the end. Okay, menti is there at the end. Menti is there at the end. Okay, so let's begin. Okay, so what can you see on your screen now? What is there on the screen now? Which thing can you see now? Here, what can you see now? There is a red color and a gray color separation. What is this structure known as? What is this structure known as? Yes, magnet. So this is a magnet. N denotes, yes, magnet. Correct. Bar magnet. Yes. So N denotes for the North Pole. S denotes for the South Pole. Fine. So this is the South Pole of the magnet. This is the North Pole of the magnet. So now we will study what is a magnet, or rather we'll study what is the definition of a magnet. So what is meant by a magnet? Let's see. So magnet is a substance which attracts substances that is made up of iron, cobalt or nickel. Fine. So when a magnet is tied by a thread and it is suspended, it comes to rest in the north and south direction. North south direction. The north pole points towards the geographical north, while the south pole points towards the geographical south of this. Fine. Okay. Till this part clear? Till this part clear? Clear with this part? Write in the chat. Clear? Clear or not? I'm waiting. Okay. So this is meant by, what is the definition of magnet? Moving. What can you see on your screen now? Okay, fine, clear. Now what can you see on your screen? There are certain substances which are attracted onto the surface of the magnet. This is a magnet, this is a magnet, this is a magnet, this is a magnet. So you can see this is a safety pin, this is something disc like. Yes, this is a horseshoe magnet, or it is called a U-shaped magnet. Fine. So this is a substance that is iron. This is also something made up of iron, right? So these substances are attracting. Okay. So what we'll study in this slide? We'll study in this slide uses of magnets. So uses of magnets used in radio and stereo speakers, used in refrigerator doors. It is used on audio and video cassettes players, used on hard disk and floppies of computer. Horseshoe magnet, yes, attracting needles. Needles are generally made up of iron only. Okay, iron and nickel sometimes. Okay, so these are the uses of magnets. So the uses of magnets are radio stereo speakers, refrigerated doors, audio video cassettes players, hard disk floppies computers, children's toys. Fine, let's move on. Who is this person? Who is this person on the slide? Who is this person on the slide? Anyone, write in the chat box. Who is this personality in the picture? Who is this personality in the picture? Let me know. Hans Christian. See, the spelling is not osteroid. It's Oersted. Okay, Hans Christian Oersted is the spelling. Oersted. Okay, it's no idea. Okay, so obviously there's no idea. This is Hans Christian Oersted, who is one of the leading scientists of the 19th century, who played a crucial role in understanding. Yes, Hans Christian Oersted, who played a crucial role in understanding the electromagnetism. That means how electricity and magnetism, these two phenomena, are related to each other. Fine. So in 1820, he accidentally discovered that a compass needle got deflected when an electric current was passed through a metallic wire placed nearby. Okay. Through this observation, Oersted understood that electricity and magnetism were related to each other. Okay, they were related to each other. Okay, so since they were related, his research contributed for the development of radio, television, and fiber optics. Okay, so the unit of magnetic field strength is named as Oersted in his honor. Fine. In his honor, it is named as Oersted, the unit of magnetic field strength. So you need to remember this. The unit of magnetic field strength is, so the unit of magnetic field strength is what? Oersted. I am writing in the chat Oersted. Okay, Oersted is a unit of magnetic field unit. So you need to keep in mind. Let's move on. Now what can you see on your screen? Now what are you able to see on your screen? Now you can see on your screen there is a part which is termed as lines, magnetic field lines, and a magnetic field. Right? So these lines that you can see on your screen is termed as magnetic field lines, and the lines which are going till this portion, full portion, is termed as a magnetic field, because the power of magnetism, or the power of that magnet, is whole. Okay, that means this full part is covered by that power of the magnet. Fine. So this is a magnet, and this is the south pole, this is the north pole. Fine. So this is the magnetic field and field line. So it is the region around the material or a moving charge within the force of magnetism acts. Okay, so magnetic field lines are a visual tool used to represent magnetic fields. They can describe the direction of the magnetic force, and as you can see in the background of the slide. Fine. Everybody has got it. Whoever is there in the class, have you all understood this topic? You have understood this part? You have got this part, magnetic field. And what is magnetic field line? So magnetic field is the part in which, yes sir, okay, okay, so magnetic field is the part, or is a region rather, in which the magnetism acts, force of magnetism acts, and the lines that are used to represent is termed as magnetic field lines. So let's move ahead. Okay, so let's now see, we will study more about magnetic field. We will study more about magnetic field. So let's see. Magnetic field is a quantity that has both direction and magnitude. It is having both direction and magnitude. As you have seen, magnetic field is having a direction, like north, south, east, west direction it will go, right? And it is having a specified magnitude, which you will learn when you will go higher. Okay, so the direction of the magnetic field is taken to be the direction in which a north pole of a compass needle moves. So the direction of the magnetic field is taken to be the direction. So the magnetic field means in which direction it will go is the direction in which the north pole of the compass needle moves. Fine. So therefore it is taken that the field lines emerge from the north pole and it merge at the south pole. Fine. It starts at the north pole and its end at the south pole. It is starting from the north pole ending at the south pole. मेंटी कब है? डियर मेंटी है लास्ट में, मेंटी है, मेंटी लास्ट में है डियर, मेंटी लास्ट में है, मेंटी लास्ट में, कोई प्रॉब्लम नहीं है, मेंटी है, चिंता मत करो, 5 क्वेश्चन का मेंटी है लास्ट में। ओके। सो कन्वेंशन से लिया जाता है कि ये फील्ड लाइन एमर्ज होता है कहाँ से? नॉर्थ पोल से शुरू होता है और एंड होता है साउथ पोल में जाके। ठीक है। अब मैग्नेट के अंदर की बात हो रही है, तो मैग्नेट के अंदर क्या होता है? जस्ट रिवर्स होता है। मैग्नेट के अंदर रिवर्स होता है, मैग्नेट के अंदर होता है south pole to north pole. Inside the magnet, it is just reverse. That is from south pole to the north pole. That is why the magnetic field are closed curves. That means they are closed. Okay, they are closed curves. Fine. So let us read the properties of magnetic field lines. Let's read the properties of magnetic field lines. They do not intersect each other. They cannot intersect each other. They can never intersect each other. Okay. Now somebody please tell me why can, if suppose let us take, if they intersect each other, then why it is not considered or it cannot exist? Tell me why it cannot exist, why they cannot intersect each other. Let me see who gives the proper answer in the chat. Write your answer in the chat. Let me see. Write in the chat. I'm waiting. Why the magnetic field lines they cannot intersect each other? Intersect each other. This is a very good question, and the answer is also very good. Okay, so let's see who answers this correctly. Okay, so you all don't know the answer. If you don't know, then there's not a big problem. Let me tell you the answer of this question. The answer to this question is the intersect. See, if these two magnets intersects each other, if the two magnets will if the two magnetic field lines will intersect, then the needle, no idea, fine, fine. Then the needle, the compass. Suppose, okay, I'll draw and show you. So just give me 1 minute. I'll draw and show it to you. Okay, just give me 1 minute. I'll draw and show it. Let me go to another PPT. I'll go to another PPT and I'll draw and show you. Okay, so stay here only, don't leave. So just 1 minute. This is just 1 minute. Yes, now it's fine now. Okay, so now see this PPT. So let us take a magnet here. Fine. So if we are taking a magnet here, if these things they are just intersecting each other, this is the south pole. Just 1 minute. This is the south pole. This is the north pole. Okay, fine. So inside the magnet, it is like this. The ray is like this inside, and if it is outside, then the ray is like this. Fine. Outside the magnet, the ray is like this. Inside the magnet, the ray is straight. That is from north to south outside, and from inside south to north. Now, if any one of these will intersect with each other, what will happen? The compass needle will have to point in two different directions at the same time. Okay, they will have to put, they have to point out the same direction at the same time. Suppose it is in northeast. Okay, so the compass cannot point at only one direction at one time. It can only point at one direction. How will it point in two direction, which is not at all possible? So since pointing at two direction is never possible, we cannot say that it will never intersect. So it cannot intersect, it will never intersect. Okay, it will never intersect. Fine. So this is the main reason behind why we are saying that it can never intersect. Fine, got it. So let me go back to that PPT again. Okay, so now I hope you can see again. So they cannot intersect each other because the properties of the magnetic field line, they are different from those of others. Okay, so due to this reason they cannot intersect each other. As I told, they have to point into different directions. Next is, magnetic field emerges from the north pole and it ends at the south pole. I have already told this, that inside the magnet it starts from south and ends at north. Outside the magnet it starts from north and ends at south. Fine. See, inside the magnet direction is from south to north, outside from N to S. Okay, so they are closed curve. As you have seen, they are starting from somewhere, ending at somewhere, so that means they are a closed curve. Okay, now what is, now you can see on your screen, you can see a clock is there on your screen, but there is a question mark. That means you have to find out the time of the clock. You have to find out the time of the clock. That means there is a question now. Okay, so answer the question. This is page number 224 question on your screen. Okay, so why does a compass needle get deflected when brought near a bar magnet? Why does the compass needle get deflected when brought near a bar magnet? Who knows the answer? Please write in the chat. If you know the answer, write in the chat. If you know the answer, write in the chat. What is deflected? Deflected means, suppose it is pointing at one direction, it is shifting from its position. Okay, it is shifting from its position. Okay, it is shifting from its position or changing its direction. Right, that is the meaning of deflection. Okay, so why does a compass needle get deflected when brought near a bar magnet? Who knows the answer? Write in the chat. Write in the chat where who knows the answer. I'm waiting for the answer. Okay, so no one knows the answer. Then let me say the answer here. Okay, so the compass needle get deflected when brought near a bar magnet because the compass needle, it also has a magnetic property of pointing towards the geographical north. So this is a property of the needle, and bar magnet when suspended also points towards the geographical north and south. So due to this reason, repulsion occurs. Repulsion, you can say rather repulsion is occurring, and due to that, the bar magnet is heavier, compass needle is lighter. Since this is lighter, it is getting shifted or distracted from its original position. Okay, so answer time. So see the answer. Magnetic compass needle and bar magnet both have magnetic field. When they both near to each other, these magnetic fields interact each other, giving deflection in the needle. That means repulsion is occurring, and due to that repulsion, the needle which is lighter is getting deflected. Fine. Reason is clear with this? Okay. So now what can you see on your screen? This is the electrical conducting conductor. Okay. This is a electrical conductor. This is a force. This is the field. This is the current. Okay. This is the current. This is the field. This is the force. This is the conductor. So now topic comes is magnetic field due to a current carrying conductor. So the magnetic field that is produced due to a current carrying conductor. Okay. So due to this, what is happening? When this is coming, see the diagram. See, this is a compass needle placed with its arrow pointing towards the geographical eastern side, not probably eastern, northeastern side. Okay, fine. So the current direction is this side, this like this way. The deflection of the current is this way. Fine. So the pointing is towards northeast. Fine. Now see the another diagram. Now you see the current direction is reversed. The current direction is reversed. That means it was this way. Now it is just the opposite this way. So what is happening? It was pointing towards the northeast. Now it is pointing towards the northwest. So are you concluding from here? That whenever a current is reversed, the deflection produced is also reverse. Okay. When current is reversed, the deflection is also reversed. So this is the thing that you can conclude from this portion. Okay. Now you see, this is a cylindrical shape. This is a cylindrical shape, cylinder rather. Okay. So this is straight E. This is naming tensor. Okay. So now you'll be coming magnetic field due to a current through straight conductor. This is a straight conductor, cylinder in shape. This is a straight conductor. Fine. So magnetic field due to a current through a straight conductor. So see, it consists of a series of concentric circles whose direction is given by the right hand thumb rule. Now what is the right hand thumb rule? We'll be coming to it a bit later. Okay. Next one. If the current is increasing, deflection produced also increases. This is very important point. If the current is increasing, deflection also increases. So remember this, fill in the blanks can come. Okay. Third point, it indicates the magnitude of the magnetic field. That means how much strength is the magnetic field produced at a given point increases. So see, magnitude increases as the current is increasing. So if the current is decreasing, then the magnitude will also decrease. If the current is increasing, then the magnitude will also increase. Fine. Last point. The magnetic field produced by a given current in a conductor decreases as its distance from it increases. Magnetic field. Now, going on, if the distance is increasing from the magnetic or the magnet rather, the magnetic field strength will decrease, right? So, if the distance is increasing, then the magnetic field produced will decrease. Okay. So what you learn from here, current increases and deflection also increases. Magnitude of the magnetic field produced at a given point increases if the current increases. The magnetic field produced by a given current in the conductor decreases as the distance from it increases. Fine. Now see the diagram. This is your hand. This is your right thumb, right hand. This is your thumb. This is your wrapped fingers. This is a stick, not a stick. This is the current carrying conductor. So this is the current carrying conductor. This is the wire. So now you are placing. This is the paper. This is the wire. Means just a drawing. So this is the way you are holding. So this is a magnetic field. This is the electric current I. This is a paper magnetic field B. Okay. So this wrapped fingers and this right thumb is showing you the direction in which the electric current is flowing, and these wrapped fingers show the direction of the magnetic field. This is what is the meaning of the right hand thumb rule. See, The right hand thumb rule is if a current carrying conductor is held in your right hand such the thumb points towards the direction, then the wrapped finger show the direction of the field lines. As I already said, the wrapped finger will show in which direction is the magnetic field going. Fine. This is what is the meaning of the right hand thumb rule. So this diagram is also there. Let us come. This is the strength of the magnetic field at the center of the loop. Now we are coming to the loop portion. Okay. Strength of the magnetic field at the center of the loop depends on three factors. The factors on which it depends, you have to remember. See the factors: the radius of the coil, the number of turns in the coil, the strength of the current flowing in the coil. These 3 points are very, very necessary. So this is the strength of the magnetic field. Center of the loop depends on the radius, number, and the strength. So this is a very, very important point. The radius of the coil. The strength of the magnetic field and the radius of the coil is inversely proportional. Inversely proportional means if one is increasing, the other one will decrease. And if other one is decreasing, the other one will increase. So if the radius increases, the magnetic strength at the center decreases and vice versa. Fine. Number of turns in the coil. As the number of turns in the coil increases, the magnetic strength at the center of the coil increases because the current in each circular turn is having the same direction. Thus, the each turn adds up. Each of the turn is adding up. That is why we can say that if the coil is increasing, the magnetic strength at the center increases because the current in its circular form is having the same direction which adds each other. Fine. Just 1 minute. I think there's some problem. Just a minute. I think there is some problem. Yeah, now it's fine. Now it's fine. Yeah, okay. So the number of turns in coil. So as the number of turns in coil will increase, the magnetic strength at the center increases because each current is having the same direction that which turn will add up. Right? Okay. So the strength of the current flowing in the coil. As the strength of the current will increase, the strength of the magnetic fields also increases. Fine. So as the strength of current increases, the increased strength of the magnetic fields also increases. Now who is this personality? Now who is this personality? Now who is this personality? Write in the chat who is this personality? Who is this personality? He is James Clerk Maxwell. Okay, he is James Clerk Maxwell. James Clerk Maxwell, who discovered or proposed his Maxwell's corkscrew rule. Maxwell's corkscrew rule. Fine. So this corkscrew rule states that if we are driving a corkscrew in the direction of the current, then the direction of the rotation of the corkscrew is in the direction of the magnetic field. So in the direction of the corkscrew, we will see that in the direction only it will go. Fine with that? Okay. So the direction of the rotation of the screw is the same as that of the direction of the magnetic field. Okay, this part is I hope is clear. Let us move on. Now we are coming to the last topic for today. Then we have a menti. Okay, fine. Okay, 5 minutes, sir. Okay, 5 minutes. 5 minutes for what, Hanika? Hanika, 5 minutes for what, dear? Dear, 5 minutes for what? Okay, so electromagnetic waves in a solenoid. What is a solenoid? Solenoid is if the coil for many turns of insulated copper wire is wrapped in the shape of a cylinder, then it is called a solenoid. The magnetic field that is produced by the solenoid is similar to that of a bar magnet. Okay, so the strength of the magnetic field is proportional to the number of turns and magnitude of current. Okay, the magnetic field lines in the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same size at all points inside the solenoid. Okay, a strong magnetic material is used to magnetize material like soft iron, etc. when this placed inside the coil. Okay, so the magnet that is formed is termed as electromagnet, which is a temporary magnetization. Electromagnet is a temporary magnetization, right? Electromagnet is a temporary magnetization. Okay, after some time it will again lose its magnetism, right? So it is a temporary magnetization. Okay, let's move on. Question time is there. Page 228 questions. Draw magnetic field lines around a bar magnet. List the properties of magnetic field lines. Why don't two magnetic field lines intersect each other? Answers are also here. Question number one answer. This is a bar magnet, south north. So you have to be very careful with the arrows. The arrows should be from north to south outside and south to north inside. Okay, so north to south and south to north. Fine. You have to be careful with this. Next question answer is here. These are the properties of magnetic lines of force. Okay, that is outside the magnet. The magnetic field lines are directed from the N pole to the S pole. Inside it is from S pole to N pole. The magnetic field line at any points in the direction of the magnetic field line of that point meet at any points in the direction of the magnetic. Fine. The relative strength of magnetic fields is given by degree of closeness of the field lines. The magnetic field is strong in the region where the field lines are crowded. If it is more crowded, that part is more stronger. So no two magnetic field can ever intersect with each other. That means no magnetic line can ever intersect. Question number three. No two field lines can are found to cross. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is never possible. As I already said, if it points in two directions, then it is not possible. Fine. Question. So consider a circular loop of wire lying in the plane. Let the current pass to the loop clockwise. Apply the right hand rule to find out the direction of the magnetic field inside and outside of the loop. The magnetic field in a given region is uniform. Draw a diagram to represent it. This question MCQ we will do in the menti. Okay. This is the answer for the question. The magnetic field lines have been shown. So this is a magnetic field line through a loop. Okay, outside the loop, it is out directed out of the plane paper. Inside, it is directed inside of the plane paper. Fine. Next. This is the uniform magnetic field represented by parallel equidistant lines. This is in a solenoid. This happens in a solenoid. Okay. Next question. Okay, so your Diwalis are coming. So today our all topics are covered that topics that are given in the description, all of that are covered for today. So what we'll do now, we have a menti. Fine. So now we will be doing one simple menti. So whoever are there, join the menti quiz and a happy Diwali to all of you. So stay safe and stay healthy. Okay. So here is the menti code on your screen. So the menti quiz is code is 4109477. Okay, so everyone, those who are there in the menti, now watching live, then join the menti quiz. Okay, so for today, thank you for attending the class. Let's now go to the menti quickly, and then we'll do the menti quiz. Okay, so thank you for joining the class. Let's do the menti, and we'll quickly wrap up the class. So here is the menti on your screen. First question will start. So join fast. Question 1 of 5 on your screen. Okay, so only one of you, one only is here in this class, so no problem. Let's start. Only Hanika is there. Okay. So which one of the following correctly describes the magnetic field near a long straight wire? So answer, see an answer correctly describes the magnetic field near. No. The correct answer is they are centered on the wire. Okay. Straight long wire it is told no, then how can it be parallel? It is parallel only in the case of solenoid that is circular. Okay, this is concentric circle centered on the wire. Okay, so next let's see the leaderboard. Okay, leaderboard, the same condition is there. Now what happened? Sorry, just a minute. Yeah, it is moving ahead. I am not able to understand. Anyways, so answer the question number 2 on your screen. So answer the question. Which of the following is incorrect? Which of the following is incorrect? Which of the following is incorrect? Inside a magnet, the line starts from North Pole and let me see. Yes, correct. Inside a magnet, it starts from South Pole and end at North Pole. This is wrong statement. Leaderboard on your screen next. So let's see the leaderboard. Okay, so only one person is there now. I don't know what had happened to the others. Anyways, so question number 3 out of 5 on your screen. The magnetic field inside the long straight solenoid carrying current is 0, decreases as we move towards this end, increases as we move towards this end, same at all points. Let me see. No, no, no. It is same. In case of solenoid, it remains same. Okay. It's okay. If it is solenoid, then it remains same in all point inside. Okay. Question number 4. Okay. Just a minute. This is question. Okay. So question number 4 on your screen. If the current through the wire increases, the magnitude of the magnetic field produced at a given point increases, decreases, remains same, all of the above, none of the above. 30 seconds time you have to answer. So think and answer. Yes, correct. Very good. It is increasing. If the current increases, then the magnetic field produced also increases. Next question. Last question. Question 5. If the radius of the coil decreases, the magnetic strength at the center decreases, increases, remains same, or none of the above. No, no. I had clearly told if the radius of the coil is inversely proportional to that of the magnetic strength. So if the radius of the coil increases, then it will decrease. If it is decreasing, then it will increase. So increases is the correct answer. So Hanika has won. She is only the one who has attended the class. Okay, so we end our Menti here for today. We end the YouTube session also today here. Okay, so all of you, those who have attended the class, a like is mandatory. Okay, so don't forget to give a like. And for today, goodbye. Hope stay safe and stay healthy. Okay, fine. Okay, so goodbye. Have a great day. Okay, so I'll stop the live streaming now. Thank you, Anika. And then you all leave a comment. You all leave a comment. You all leave a comment in the comment section. You all leave a comment, not in the live chat. In the comment section, leave a comment. There is a part called comments. Leave a comment in the comment part. Okay, not in the live chat. Fine. Okay. So bye, bye everyone. Bye. So now, bye.